Right, good day. Welcome to Power Machines N5 online class. So uh, today's topic is about the steam condensers. So hopefully from the previous chapters, we came across a steam plant. We know that for steam plant, you will have a boiler where the steam will be generated. Then from here, you will have the steam will be sent to the turbine. Then from the previous lessons or chapters, we had this chapter called turbine. So from the turbine, the steam will move to, will enter this stage or this component called the condenser. So from the condenser, we know the function of the condenser is to change the form, which is the vapor or steam. We change the steam to the liquid or to water. So at exit here, we're going to have the steam. So somewhere here, we're going to have the pump, which is going to push that water from one point to another point, and in that way, it will also raise the pressure of that liquid. So the liquid will be sent back to the boiler. Now, today we are not interested with the whole plant, with this steam plant, but we are only going to focus on this component, which is the steam condenser. Right, if you like, you can call a condenser a heat exchanger. So meaning that we're going to have two things there. So we're going to have the vapor or the steam, and then we're going to have the liquid. So we're going to have two things. So these two things, they are going to exchange. They're going to exchange the heat energy. So one of them is going to receive the heat, and then while the other one is going to lose. So they will exchange in that way. So we're going to have the steam entering this at this point. So this steam will be coming from the turbine. From the turbine, the steam will enter here. So this steam will be, can either be wet or it can be dry or it can still be superheated. So the question will have to give us more information there. Right, the steam will be hot. So it will depend as well. But when the steam enters here, the steam will be hot, meaning that it's going to have the heat energy. So now, since the steam will be hot, inside these pipes that you see here, we can call them the tubes, these things. We're going to have, I can say, almost the cold water inside these tubes here. We're going to have the cold water. So the steam is going to heat or is going to come in contact with this material, this tube here. Inside this material is maybe warm water or cold water. So that water inside this tube, the water is going to absorb that heat energy from the steam. Then in that way, the steam is going to lose the heat energy. So that heat energy will be transferred to the water. So that's why we call this thing a heat exchanger. Because these two things, which is the steam and the cooling water. So here's the cooling water. The cooling water will be warm or cold as it enters here. And then it will be pushed by the pump. It will enter like this. Like this, let me use a more visible. So the water will enter like this. like this, like that, and then enters via this, via these tubes here. Then they will exit here. The water will come this side. This one is a baffle, or it's just a barrier. It blocks the water from passing into that other side. This water won't pass there. They will just hit here and then take this direction and enters this space here. Then the water will pass into this side. When it comes this side, it will hit this surface here. Then it will change direction and still enters here. Take this route like that, and then the water will exit there. So this is the cooling water coming in. So the water, let's say it will be cold, and then somewhere here, this water as it passes here, uh, it's going to be surrounded by the steam, which will be hot. That steam will be hotter. So in that way, this cold water, since remember the heat always moves uh, from high temperature to a lower temperature. So the heat energy will move from the higher temperature to a lower temperature substance. So the high temperature substance is going to be the steam. The lower temperature substance is going to be the cooling water. Therefore, the heat will move from high to lower temperature substance. So this water will absorb that heat energy from the steam, that meaning that the temperature of this water will increase. So that heat energy absorbed by this water will be coming from the steam. So we must expect that maybe, let's say, if the temperature of this liquid at entrance is 20 degrees Celsius, then we must expect the outlet temperature to be more, maybe 60 degrees Celsius. So the same thing with the steam, maybe the steam, when the steam exits the turbine and enters this condenser, maybe the steam will be having this temperature. But along the way, as the steam hits the surface of these tubes, the surface of these tubes will be quite warm or cold because it will contain water inside. So that coldness is going to affect the steam. Then the steam is going to lose the heat energy. Then that heat energy will be absorbed by the cooling water. Then in that way, as the steam loses the heat energy, then there will be the change in phase. The steam will change from vapor or from steam to the liquid. So to change that steam to liquid, uh, we will reach that, or we'll arrive to that by reducing the pressure. Remember, the pressure in this condenser, we say it's vacuum. We say it's negative. Or in other words, the pressure in this thing is going to be below the atmospheric pressure. Remember, atmospheric pressure is 101. So the pressure in this condenser is going to be below that atmospheric pressure. So due to that pressure, the lower pressure, and then due to the drop in temperature of the steam, condensation will occur. So now along the way, that steam will change the phase. You will find that somewhere here, the steam will no longer be wet steam, but it will start to turn into water, into liquid. So when it reaches this point here, it will be full liquid. So let me use this yellow one. This yellow one represent the steam from the turbine, and then the green one will be represent the cooling water. Right, so these are the tubes. It's just that this one, maybe it's a front view. The 3D, in 3D, whatever that you see here is this one here. So these are the tubes, more like the pipes. It's like a pipe. Then through these gaps of this pipe, the water will enter there, the cooling water will enter there. Then we know that this water now from here, it will be transferred back to the boiler by the feed pump. So we can call this thing the feed water. We can call it the feed water. Right. And now what's happening with this software? I'm having the technical challenge here. Right, sorry for that. So we're going to have actually two types of condensers. So this kind of condenser, we're going to call it the surface condenser. This one here. We're going to call it a surface condenser. So what's happening with the surface condenser is that uh, there will be indirect contact between the steam and the cooling water. So they won't really touch each other or mix with each other, these two. So since they will be separated by the pipes or the steel, so between the water and the steam, between you see this black line here, it's a tube, it's a steel. So if inside here is water, this red part represents the water. Then there will be a steel there and a steel there, which is this black line. And then on that outer surface of that steel is going to be the steam. So they won't directly touch each other. The steam and the water, they won't directly touch each other. So that kind of condenser, we call it uh, surface condenser, which is having the indirect contact. So the other one, we can have what we call the condenser, jet condenser. So with jet condenser, so with jet condenser, you will have something like this. Jet condenser. So you will have this component which is going to receive the steam from turbine. Then we're going to have another pipe or inlet here, which is going to transport the cooling water. So this will be the cooling water. And we're going to have this component here. can call it the well or whatever. So what will happen is that here is going to be water, cooling water. It will travel via this pipe and go enters this. So the water will be pouring like this. And as it enters there, simultaneously, there will be steam entering. Steam entering from, this steam will be from the turbine. So from the turbine, the steam will enter this side like that. Then these two, I'm referring to the steam and the cooling water, they will mix. They will mix in this thing, in this whatever component, this component here. These two water and this thing, they will directly mix. They will directly mix. And then after that, via the pump, this liquid, which is the mixture of that steam and the cooling water. So remember, once this water comes in contact with this steam here, the steam will condensate. There will be condensation. The steam will change the phase from steam to liquid. So now you will no longer have a steam here. You will have water. So that water will come to this and maybe fill up to this level. So this will be water. There won't be steam here. Then from here, certain portion of this water will go back to this. We can call it cooling tank. And then certain water will be taken to the boil. Certain amount of water will go back to, will be sent to the boil. Right. So that is a jet condenser. So the difference with this one is that this one, the steam mixes, comes in contact, direct contact with the cooling water. Right now, before we can calculate most of the things, firstly, you'll need to know the pressure in the condenser. So to calculate pressure in the condenser, we're going to use these two, I can say, gauges. So they're called the manometer. This one is the manometer. This one is the barometer. So this one, manometer, is used to measure the pressure of the gas in a low pressure system. So which is in our case, which is the condenser. Remember, the condenser is going to have the lower pressure. As I've said, that the pressure in the condenser is going to be low. So to measure the pressure in a system where the pressure is low or where the pressure is below the atmospheric pressure, in most cases, we prefer to use this. So how this one works is that you will take one side of this. You can see we have these two sides. So maybe let's say you want to measure the pressure in the condenser, then you take this pipe into the condenser, and then this one is open. This one maybe it's open to the atmosphere, this pipe. So you open it to the atmosphere. So you will see this thing will be pushing each other. So the atmosphere will push like this, and then the pressure from the condenser as well is going to push from this direction like this. So as these two pushes from both sides, this is mercury. Starting from here up to this gray thing here is the mercury. So the mercury will move. It either will move going up or coming down, depending on which one is. So this is the pressure difference from here to there. It represents the pressure difference. So this measurement that we're going to find here is going to be what we call the gauge pressure. So this height here, maybe you'll get, maybe I don't know, 105 millimeter of mercury. So once we have this, which will be this, that will give you the gauge pressure in the condenser. Remember the gauge pressure. So what is gauge pressure? If one end is open to the atmosphere, the height difference is the gauge pressure. So the height difference, which is this, is going to give you what we call the gauge pressure. So that is the pressure in that condenser put into this measuring instrument. Right. If you want to know to measure the pressure of the atmosphere, if you want to measure the pressure of the atmosphere, we use this mercury barometer. So once they mention the barometric pressure, you must know that they're talking about the atmospheric pressure. So this barometer is used to measure the atmospheric pressure. So as you can see, this one, it will be exposed to the atmosphere, then that atmosphere will push this mercury here. As it pushes this mercury will rise. Then it will rise to a certain value there, maybe 7.6 centimeter, which is 760 millimeter. So 760 millimeter of mercury is going to give you the pressure, the atmospheric pressure. So this device, it's for measuring the gauge pressure. So I can say the gauge pressure is going to have two units. It's either you can use millimeter Hg of mercury. Then if you want to convert it to kPa, I will show you. This one as well is the pressure. This one is atmospheric pressure. This will be the atmospheric pressure. So now you just have to convert these two. Remember, let me try to find the new page. But I still want to see this. What must I do? Let me see if I can go down. I can't go down. I'm looking for space to write. Right, 700 and of mercury equals to 101.325 kPa. So now, if you go back to this problem, I'm not sure if I should do this or see that the part of converting this. Let's leave this part. We'll meet it when we do calculations. So, but you are going to use this to change the pressure from millimeter of mercury to kPa. So it's like, let's say from that thing that I've shown you there, from this height difference here, let's say from this height difference here, you get Uh, let's say you get 76, or no, let's say you get 80. So you get 80 there. So you want to convert that 80 to, you want to convert it to kPa. So to get do that, you will cross multiply this one multiply by this one multiply by that. And then maybe here you can call it x. So when you cross multiply, you will have x multiplied by 760 equals to 80 multiplied by 101.325. Then x will be equals to 80 multiplied by 101.325 over 760. So in short, you can simply say to convert the millimeter of mercury to kPa, you can simply just take that millimeter of mercury multiplied by 101.3 over 760. So that's how you will convert that millimeter of mercury to kPa. So this one you'll get it from the manometer that had is that height difference. So take that height difference which represent the pressure, which represent the gauge pressure, and then you multiply it by this. Then that's how you convert that millimeter of mercury to kilopascal. Now we're going to have the gauge pressure, and then we're going to have absolute pressure, we're going to have atmospheric pressure. So we're going to have three things. So hopefully you are familiar with this one, this formula here. Absolute pressure, which is the total pressure. Absolute pressure equals to the gauge pressure. The gauge pressure is that height difference, as I spoke about it before. We're not going to use this, but let me talk about this since you are used to this. Plus the atmospheric pressure. Atmospheric pressure is obvious. So this one, we will only use this one if the gauge pressure is above the atmospheric pressure. Like in our scenario, we said that the condenser, the pressure in the condenser, it's vacuum, meaning that is negative. Negative meaning that is below 101.3 kPa. The pressure in the condenser is going to be below 101.3 kPa. So the pressure below 101, we say that pressure is it's vacuum or it's negative. So because of that, due to the fact that in the condenser we're going to have the negative pressure, then that's why here you are going to have negative here. So now the absolute pressure, which is the total pressure, is going to be equal to atmospheric pressure minus this vacuum pressure or the gauge pressure. If you want to use plus, is fine, but it means that here you are going to put negative. Why you have negative is because that pressure will be below the atmospheric pressure, and it will lead you to this. But maybe for this section, maybe forget about this. The pressure in the condenser will always be negative. So the absolute pressure is going to be this one. So while we're still on those two gauges, the manometer one, we use it to measure the pressure of the liquid or the steam in an enclosed system, which is going to be the condenser. This one, barometer, is going to measure the atmospheric pressure. So once they mention a barometric pressure, sometimes they will give you, they will say blah, 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 barometric pressure equals to this. You must know that they are referring to this atmospheric pressure. Barometric pressure equals to atmospheric pressure. So the other difference between these two is going to be this. Manometer will have this U-shape tube, and then the barometer will have a vertical tube like this one. So we've already seen it there. Here we go. Here's that vertical tube. Then here is that U thing. So that is one of the difference between the two. So now, as I've said, we are going to need the total pressure or the absolute pressure or the actual pressure. Then to get the absolute pressure, you must add the atmospheric pressure to the gauge reading pressure. But as I've said, on our side, the gauge pressure is going to be negative for condenser. Then it's going to be minus always. So maybe let me make some sense with these three pressures. Okay, let me consider this. Remember this, okay, let's say this one is open to the atmosphere, this one, this side. This one is connected to the condenser. Sorry. Right. If these two sides applies the same pressure, what will happen is that this mercury will drop from here to here, and then this side rise from here to there. Then if they go like that, what does it mean? It means that there won't be height difference. So if there is no height difference, what does it mean? It means that the gauge pressure is zero. Remember, the pressure that you get here from this side is the gauge pressure. The gauge pressure is zero. The gauge pressure is not telling you about the pressure in this condenser. Remember I said that there will be pressure from this side, pressure from the atmosphere. So if these two pressures are equal, then these things, they will be on the same level. So if they are on the same level, this H is going to be zero. Then if that H is zero, that means that the gauge pressure is going to be zero. Now, what will be the absolute pressure now? Okay, let's forget about this minus. I mean, this plus. Let's always use minus for condenser. Right. So from this to calculate the absolute pressure, you are going to have the atmospheric pressure. So which you will get from this barometer, 101.325 minus gauge pressure if they're on the same level is going to be 0. So meaning that the absolute pressure is going to be 101.3. So this is the pressure in the condenser in this thing. So if this thing is 0 here, it will be wrong to say that it means that the pressure in the condenser is 0. No, the pressure in the condenser is not 0. It's not 0. That's why these things they're on the same level. It's because there is pressure coming from this side, pressure coming from this side. So if they're having the same magnitude, this thing will be here on the same level. So if you've got 0 pressure here or 0 height difference, it doesn't mean that there is no pressure on both sides. The pressure is there. So the pressure in the condenser is there. So now to calculate this actual pressure in this condenser, which is not 0, to calculate this pressure in this condenser or this actual pressure or this total pressure, we are going to say the atmospheric pressure minus the gauge pressure. So in this case, the gauge pressure is 0. Then that means that it will mean that the pressure in this condenser equals to the atmospheric pressure as I've said. Or as long as these things are on the same level, it means that the pressure on this side equals to the pressure on the other side. So you must never take this pressure from this H as the pressure in the condenser. No, this pressure here doesn't represent the actual pressure or the absolute pressure in this condenser. So otherwise, if you take this as the pressure in the condenser, then that means here you are going to have 0, which is not right. So just be careful of that. So I was just trying to make the sense from uh, these 3 types of pressures. Right, I'm going to explain some of the things or most of the things as we solve the problem. I'm trying to save time. I don't want this video to be that long, otherwise it will be too long. So if I do the introduction, I come back and solve and then it will be too long. So I will solve the problem while explaining or while introducing at the same time. Now let's check this problem on the screen. Blah 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 blah. Okay, I'm going to try to feed this given data onto the sketch or picture. Okay, from that question that you saw on the screen, a dry saturated steam is received by the surface condenser. We know what is a surface condenser at a mass flow rate of 5,400 kg per hour. So the steam will enter here, meaning that every hour the steam that will pass here is going to be 5,000 kg per hour. So that is going to be the mass flow rate of the steam. So the mass flow rate of the steam is I do have calculator here, but I'm not. I will try to do it behind the scenes to save time. So maybe you can convert this to kg per second. So that's what you're going to have, meaning that every second 1.5 kg of steam will pass here. Every second 1.5 kg of steam passes. Okay, back to our question statement. The mercury manometer reading. Remember, mercury manometer gauge or reading is going to give us the gauge pressure. So it's 700. So is this one 700? While the barometer reading, which is the atmospheric pressure, is this much. Now calculate the absolute pressure. I'll try to do it here. Remember, I said that the absolute pressure equals to the atmospheric pressure minus the gauge pressure. The gauge pressure is that one of the height difference, which is that one that we get from the manometer reading. So the atmospheric pressure is going to be this one from the barometer, 760 minus the gauge pressure is going to be this one from the manometer, which is 700. So this will be millimeter of mercury. So now to convert this to kPa, as I've said, I've shown you before, then you just multiply this thing by 101.325 over 760. I didn't open my calculator here. So you will have maybe 60 multiplied by 7.999. So we can round it and say is 8 kPa. Remember it's K because this 101 is in K. Then we are done with the first question, the absolute pressure in the condenser. We are done in that way. Now, question 2, calculate the heat lost by the steam. So before we calculate the heat lost by the steam, maybe let's go. I think we didn't finish reading the question statement. Okay, the cooling water enters. The cooling water enters at 15 degrees Celsius. So the cooling water will enter here. This is the cooling water inlet here. So this water will enter at the temperature of 15 degrees Celsius. So you can see the color is blue there. So what is the meaning of that blue color? It means that the water is cold. So this is the water will enter here. So the water will enter here. The water is cold. The water is cold. Then it enters via this tube like this. It will flow inside. So as it flows inside, it's going to experience the heat. You see this yellowish thing that you see here. This is the steam. This is the steam. So you'll find that the steam maybe it's having the temperature of 40 degrees Celsius. Then the water is having the temperature of 16, 15 degrees Celsius, somewhere there. So there will be, since these two will have two different temperatures, then there will be heat exchange. So as the water travels via this pipe, it's going to absorb that heat from the steam. So the water will be warm. So when the water reaches this surface here, this side, the water will be warm. And the water will hit this side and then takes your turn like this and then enters this tube like that. So it will flow, the water will flow like that. So as it flows like that, remember here it will be the steam. The steam will be hot. So you see this red thing here, it represents the hot steam. So the hot steam will burn this surface here, this steel pipe. Then because inside the steel pipe is water, and then the heat will be transferred via conduction to that water inside. So the temperature of the water will rise. The temperature of the water will rise, then exit here. So as you can see, the color changed now. So this orange color, it means that the temperature of the water now will be higher. I'm just giving an example. Maybe the temperature will be 70 degrees Celsius. Okay, but anyway, let's forget about this 70. According to our question, the temperature at outlet will be 37 degrees. So when the water leaves here, the water will be having the temperature of at outlet 37 degrees Celsius. So at inlet, the temperature is 15 degrees Celsius. At outlet, after exchanging the heat with the steam, the temperature of the cooling water will increase to 37. So remember, during that process, the temperature of the steam will drop, meaning that during this process, uh, the steam will lose heat. So I can say that heat lost by steam will be equals to heat gained by cooling water. So I'll write that nicely on this page. So just know that we're going to use that concept now. or no, we'll use it on number 3 maybe. So what is the second question? The heat lost by the steam. Okay, it's fine. So the heat lost by the steam, you just have to know the heat energy of the steam at entrance and then the heat energy of the steam at exit. So back to this. So let me erase this, but you are going to use it later. Just for this thing to be clean. It's not supposed to erase this, but it's fine. It's fine. Right. Now we have to find the enthalpy of this steam. Remember, at entrance here, we're going to have the steam. So according to this question, if you go to the question statement, we have a dry saturated steam. So this steam will be dry saturated. So it's not wet. It will completely be dry. No water droplets in this steam. So now the enthalpy of this steam entering this condenser at the pressure of 8 mpk. Remember, the pressure in this condenser is going to be 8 kPa. We calculated that. So if you want to know the heat energy of this steam entering this condenser, then you have to go to the steel table and check the pressure of 8 kPa. Remember we said the pressure in the condenser is 8 kPa. Then along this 8 kPa, check Hg. So you'll see that Hg is 2577. 2577. Then it means that Hg, which is the enthalpy of the steam, remember what is entering here is the steam. So the heat energy of this steam is going to be 2577. 2577 kJ per kg. So that is the steam. So the steam will enter there and then the steam is going to exit here. But at exit, it will no longer be the steam. Remember, that is the function of the condenser, is to change the phase from vapor or from steam to liquid. So this is at exit here. So at exit, you are going to have water here. So now, to find the heat, is it heat gained or heat lost? Heat lost by the steam. You have to find the enthalpy at entrance and enthalpy at outlet. So the enthalpy at outlet here, since this thing is liquid, this is the enthalpy at outlet. So since at outlet here we're going to have water. Remember, water is represented by F. So the enthalpy of this water at exit is going to be the HF. So now to find this enthalpy, you just have to go to a steel table and find the HF. So now how are we going to find that HF? We're going to use the temperature of this liquid at exit. So how much is the temperature of this liquid at exit? Remember, we've got two liquids here. We've got this one, which is the cooling water. We've got this one here, which is that one entered as a steam here. Then it changed the phase to water. Okay, when you go to back to your question, they said that the condensate is undercooled by 3.9 degrees Celsius. 3.9 degrees Celsius. So, meaning that the temperature of this steam is going to drop by 3.9 at exit. It's going to drop not 2. It's not dropping to 3.9, but it's going to drop by 3.9. So now it's taking us back to the steel table. Back to the steel table. And we're going to use that steel table to find the temperature of that steam, of this dry-saturated steam. So this dry-saturated steam is going to enter with this temperature, 41.6. This He goes with this temperature. So as that dry steam enters the condenser, the temperature of that steam would be 41.6. So I can say that the Ts here equals to 41.6 degrees Celsius. Now, how much will be the temperature of this steam at exit? So the temperature here would be equal to, remember they said that the temperature is undercooled by 3.9 degrees Celsius. So that as the steam goes down, the steam will be cooled. The temperature will drop. The temperature will drop by 3.9. So the temperature will move from, let's say the temperature here. Let me write the temperature at outlet, or the temperature of the condensate. Remember, this is the water after condensation. So you can still say the temperature of the condensate. So this temperature will be equal to the initial temperature 41.9 minus 3.9. So if we remove 3.9 from this, you will remain with 37.7. So if you drop this temperature of 49 by 3.9, then you will remain with 37.7. So meaning that the temperature of this outlet, water or condensate, is going to be 37.7 degrees Celsius. So now we're going to use this temperature to find the liquid enthalpy, the enthalpy of this liquid. Remember, this is not the steam. Now we have full water now. So the enthalpy of water, we use HF. So we go to the temperature, HF, TS. Here we go, you check 37.7. So the liquid will have at this temperature. So at this temperature, the liquid will have the heat energy of this much, 158. So meaning that at outlet, the enthalpy of this liquid is going to be 158. One 58 kg per kg. So we've used this temperature of 37.7 to find this value. Now let's calculate the heat lost. So to find the heat lost by this steam, you just have to take this, you just have to subtract these two heat energies. You just have to subtract these two heat energies. So we're going to start with this big one, this one minus this one. Then you will find the heat lost. So it's like you want to check how much you lost. Then if you want to know how much you lost, you have to know how much you had before, then how much you had after. So it's like maybe when you enter the class, you were having 10 rand. And when you leave the class during the lessons, when you search yourself, you'll find the 4 rand in your pocket. You had 10 rand when you enter the class. When you leave, you have 4 rand. So this team will had energy of 2577, and then when it leaves, it had the energy of 158. So if you have 10 rand, and then when you leave the class, you find that we have 4 rand. How much you lost today? So you'll say 10 minus 4 equals to 6. That means in the class, you lost 6 rand. Someone stole it or is on the floor or whatever. It means you lost 6 rand. Where's that 6 rand coming from? Is 10, which is what you had before, minus 4, which is what you had when you leave the class. So that means you lost 6 rand. So the same thing here, to get the heat lost, you'll say that inlet minus this outlet. So the heat lost by steam equals to, if they say specific heat loss, then we just say those two H's minus the other H. So if they say specific, then M would be equals to 1. But if they just say heat lost or heat absorbed, then you have to include this mass to get the total heat. Then if the mass of the steam is per second, remember we found that the mass of this, which is mass of the steam, is 1.5 kg per second. So if you use that, then it means that the mass is in kg per second. It means that the unit, the heat energy lost, is going to be in per second as well. So now once you multiply by mass, you will no longer have this kj per kg. So once you multiply by mass, you multiply by mass, this kg divided this kg. Right. The mass of the steam is 1.5. H inlet 2577 minus 158. Then you will get, uh, I'm not going to calculate this thing on the screen to save time. I don't want this video to be too much long. So I won't calculate it on the screen. You will do it yourself. So I can say maybe we didn't answer the question. Remember, the question is looking for the heat absorbed by the cooling water. So as we calculated the heat lost by the steam. But as I've said before, we know that heat lost by the steam will be gained by the cooling water. They will be equal. So whatever heat that will be lost by the steam will be absorbed by the cooling water. So in that way, we've answered the question. Now, number 3, we have to find the dryness fraction. Sorry, there was typing error there. Let's cancel this. Number 3, we have to find the mass rate of the cooling water required. Mass rate of the cooling water required. So remember, in this condenser, we're going to have two things entering. We're going to have the steam entering at this rate. So we're going to have the steam entering here at this rate, 1.5 kg every second. So now we want to know the rate of the liquid, of the cooling water. Remember, the cooling water has to enter as well. So now we want to know at what rate must this cooling water enter this condenser to achieve those variables, outlet variables mentioned by the question statement. So we want to know the mass of the cooling water, the rate, meaning that we want to know that every second how much liquid must enter here. Should 2 liter of this water per second enter here, or 1.5 liter, or 1 liter? So that's what we're looking for. So to get that, we'll use that concept, heat lost equals to heat gained. So heat lost by the steam will be equals to heat gained by the cooling water. So to calculate the heat gained by the cooling water, we're going to use this. Then we know that the heat lost by the steam, it will be 3628.5. So let's use the cooling water variables. Let's use this one and equate it to this. So we're going to have Q equals to M, which is going to be the mass of the cooling water, multiplied by the specific heat capacity of the cooling water, multiplied by temperature at outlet and temperature at inlet of the cooling water, equals to 3628.5. So actually we're looking for this mass. So since this thing is in kg per kg, that's why this m here as well, the answer that we're going to get here is going to be in, is in S. It's going to be in kg per S. That's how we put the dot here. We put dot here because this thing is expressed in, it's a rate, or it's expressed in terms of time. So that's why this mass here as well is going to be expressed in terms of time. So the specific heat capacity of this water, let me check if it's given. Yes, it's given is 4.13. The specific heat capacity of cooling water is 4.13. The temperatures, we've made them before. At outlet, we said is 37, at inlet is 15, equals to 3628.5. Then the mass rate of cooling water will be equal to 3628.5, all divided by 4.13, multiplied by, so you will get 39.9 kg per second. So the mass flow rate from this side is going to be 39.9 kg per second. So every second, 39.9 kg of water will enter here. Right, now let's move to number 4. What's happening here? Okay, sorry for that again. Number 4, let's calculate the number of tubes required. The number of tubes required. Let me see if I can remove this. Right, now we have to calculate the number of tubes required. So these are the tubes that they are talking about. These are the tubes that they are talking about. This one here. These are the tubes. So can you see we have here we have 1, 2, 3, 4, 5, 6, 7, 8 tubes. But in this question, we don't know how many tubes. So we have to find out. So that number of tubes will have to correspond with this flow rate, with this mass flow rate. So if the water that enters the condenser is too much, then we might need more water tubes. So if the water that enters is less, then we might need less tubes. But it will also depend on the diameter. So it will also depend on the diameter. If the diameter is big, then you only need a few tubes, even if the flow might be big. Right, already I think they told us the diameter of the tube. When you go back to the question statement, they said the inside diameter of the cooling tubes is 20 millimeter. So the diameter of this tube here, starting from here to there, this diameter here from here to there is 20 millimeter. So we have to find out how many 20 millimeter diameters of these tubes we're going to need in order to have this flow rate of 39.9. So we're going to have the formula for that. You'll get the formula from your textbook, but the formula, it's like this. N equals to V. So this is the volume rate of the cooling water. Area, the cross-sectional area of the tube. That is the cross-sectional area of the tube. Actually, it's not the cross-sectional area of the tube. It's the inside area of the tube. It's the cross-sectional area of inside of the tube. Yeah, I will write it down. Then multiply by V. So this V is the speed of the cooling water. So as the water enters that condenser, the water will be flowing at a certain speed. Now let me quickly just write this thing down. Let me use this space here. N represent the number of tubes. A represent cross sectional area. Of inside tube. It's very important, this, because the cross-sectional area of the tube is this. This is the cross-sectional area of the tube. But when we talk about the cross-sectional area of inside of the tube, then we'll be talking about this yellow part. And as you can see, this yellow part is a round profile. Then we're going to use this as pi d squared over 4. Now this is the area that you must use, not the cross-sectional area of the tube. Remember, if we have the cross-sectional area of the tube, we are going to have pi capital D squared minus this over this. So this one will give you this black area here. Will give you this black area. So we don't want this black area. We want the yellow one. Good. So V is going to be the speed of the cooling water. So as the water enters the condenser, the water will be moving at a certain speed. So that is that speed there. What is left now? Oh, W dot. So this is the volume rate of the cooling water. Volume, meter cubed, rate per second. So this is the speed, this meter per second. So these two, they are different. So this one is about how fast. This one is about the amount of liquid that enters the condenser. It's about meter cube, the amount. How many liters? 5 liters per second, 3 liters per second. This one is about the speed, the distance that will be covered by the water particles per second. This other V. So you must be careful of that. Right now, back to our question. We have to find this one, volume rate. So to find the volume rate, you will recall that from this formula of mass equals to density multiplied by volume. So if you have mass rate, then you'll have volume rate here. So to get this volume rate, we can say it will be equals to mass rate divided by the density. So mass rate we calculated is this one here. Is 39.9 divided by 1000. The density of water, they don't have to give you, you should know this one by heart. Then the volume rate, in this case, is going to be maybe 0.0399 meter cubed per second. So that is the volume rate. Remember, we're not looking for volume rate, we're looking for N. So at the moment, we have this guy. The speed it's given. So back to our question. Oh, it's up there. It's up there. It's this one. So the speed is 1 meter per second. The speed of this cooling water is 1 meter per second. So V is 1 meter per second. Now we're left with the area. But the area, we know the diameter, I think they said is 20 millimeter. Then we've got two options, remember, to calculate the area there. You can use pi r squared or you can use pi d squared over 4. So it's really up to you. So if you have diameter, maybe you can stick to this one of diameter. Diameter is 20 millimeter. Is it 20 millimeter or 20 centimeter? 20 millimeter divided by 1000, you'll have this over 4. Pi d squared over 4. Then you will have 314.159 times 10 to the power minus 6. So if you decide to use this one, remember you must use R. R will be 10. 20 divided by 2, then you'll have 10 here. Now from there we have everything. Now we just have to substitute. So back to our formula there. N equals to volume flow rate. The volume flow rate we have 0.0399 over the area is 314.159 times 10 to the power minus 6 multiply by V, the speed, is 1 meter per second. Then the final answer here, you'll have 127.117 cubes. But obviously we won't have half tube or 10% tube. We will have full tubes. So instead of 127 tubes, we're going to have 128 tubes. Right. So it's like when you go to the shop, and then maybe you want the 5 bottles. And then when you go there, they sell the bottles in pairs, two, 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 two. Then they will say they don't sell one, one. So since you want the 5, then you'll be forced to buy 6, 2, 2. 3 pairs, 2, 2, 2, it will be 6. So it's either you buy 6 or 4. So since you need 5, then it means that you have to take 6. Then you will see the other one where to use it. Okay, it's fine. Let's continue. The last question, it will be to calculate the condenser efficiency. So the formula for condenser efficiency, it's like this. T2 minus T1 over Ts minus T1. So by definition, condenser efficiency is the ratio of temperature rise of cooling water. So this one here, it should be the temperature rise of the cooling water. So this is the outlet temperature of cooling water. This is inlet temperature of the cooling water. So this is cooling water temperature rise, which is the difference of the inlet and outlet. Now is the ratio of the temperature rise of the cooling water compared to the difference. So this one below is the difference between the temperature of the steam. So that's why you see S here. So this is temperature of the steam over the difference of the temperature of the steam at inlet. At inlet of the condenser. And the inlet temperature of the cooling water. So this one is the temperature at inlet of the cooling water. So I can say inlet cooling water temperature. So I don't have to go to that picture. Hopefully you will recall that those temperatures at outlet is 37, the cooling water temperature. 37 minus inlet is 15. This one is the temperature of the steam. So I said is 41.6. So at entrance, I spoke about it. Is it 41.6 or 49.9? It's 0.6. It seems like it's 0.6. So I did mistake here. Make sure that you correct it. It's 0.6 actually. 0.6. It's 0.6. Yeah. So it's 0.6 is this temperature at the pressure of. Remember, the condenser, the pressure will be this much. Therefore, the temperature will be that one there. So that will be the temperature of the steam at entrance, which is that dry saturated steam. So that dry saturated steam will have the temperature of 41.6 minus the temperature of the cooling water at entrance, which is 15. Now you will have 82.7%. So that will be your condenser efficiency. Right, that is the end of our exercise. That is the end of our exercise. Sometimes they will ask about the vacuum efficiency. So let me just write or explain the formula of that vacuum efficiency and then stop there. I won't solve it because this video is already too long now. Yeah, here we go. So for gauge pressure, you just have to, from this formula of absolute pressure, you just have to make P gauge, the subject of the formula. So if you make P gauge the subject of the formula here, it seems like you'll have P atmospheric minus P absolute pressure. Or if you don't want to subtract the two, then P gauge. Remember I said that height difference from that manometer thing. So mercury will be go like this, and end here. So this height difference here, I said, is the gauge pressure. So that gauge pressure, you can use this height here, which is this height here, then you convert it to 101.325 over 760 to convert this thing to blah 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 kPa. So that's how you'll find this one. So the P gauge of steam will be equal to atmospheric pressure minus, let me write it in full, absolute pressure of steam at entry. So this one will be 101.325 minus absolute pressure of steam at entry. Yeah, so this is the entry. So they will be looking for the pressure at this entry. You can see is this one. So this is the pressure that you must use. We'll meet it when we solve other problems. But for now or for today, let's stop there. Thank you very much.